The James Webb Telescope is capturing light from the universe's earliest moments, and the secrets it uncovers are reshaping our cosmic story. Stay tuned, because number 1 will surprise even seasoned astronomers. Stunningly, JWST has captured light from galaxies that formed just a few 100 million years after the Big Bang, offering a direct glimpse into the universe's infancy. These primordial structures are incredibly faint, but the telescope's infrared sensitivity pierces through cosmic dust, revealing star-forming regions that were invisible to earlier observatories. Researchers estimate these early galaxies contain just a few million solar masses, far smaller than our Milky Way, yet they already exhibit complex chemistry, including heavy elements forged in the first generations of stars. By analyzing the spectral fingerprints, scientists can trace how quickly these galaxies assembled mass and began enriching their surroundings. This discovery challenges previous models that suggested a slower buildup of galactic structures, implying that the universe's first building blocks assembled more rapidly than anticipated. Each new detection adds a crucial piece to the puzzle of how the cosmic web evolved from a uniform glow into the rich tapestry we observe today.
Imagine the universe bathed in a fog of neutral hydrogen, then gradually clearing as the first luminous sources ignited. JWST is charting that transformative era known as reionization. By measuring the faint signatures of hydrogen absorption in distant galaxies' spectra, the telescope pinpoints when pockets of ionized gas first pierced the primordial darkness. The data suggest that reionization was not a uniform process, but rather a patchwork of ionized bubbles expanding around early star clusters and black holes. This nuanced view contradicts earlier theories of a smooth, rapid transition, indicating instead a staggered timeline that stretched over several 100 million years. Understanding this epoch is vital because it set the conditions for later galaxy formation and influenced the large-scale structure of the cosmos. JWST's observations also help refine simulations that predict how the first light sources interacted with their environment, offering a clearer narrative of how the universe became transparent to visible light.
Surprisingly, JWST spectrographs can dissect the light from individual stars and galaxies that existed when the universe was less than 1 billion years old. By spreading this ancient starlight into its component colors, the instrument reveals the chemical fingerprints of elements like carbon, oxygen, and iron. These elemental abundances inform astronomers about the generations of supernovae that seeded the early interstellar medium, shedding light on the life cycles of the first massive stars. The findings show that even at such an early epoch, there were already multiple generations of star formation, contradicting the notion that early galaxies were chemically pristine. Moreover, the presence of heavy elements implies that the first stars lived fast and died young, enriching their surroundings swiftly. This spectral insight refines our understanding of stellar evolution under primordial conditions and provides a direct link between the first stars and the complex chemistry that later enabled planet formation.
Few people realize that JWST has identified candidate seeds of supermassive black holes less than 1 billion years after the Big Bang. These objects, observed as compact, intensely luminous cores within young galaxies, exhibit rapid accretion rates that could allow them to grow into the monstrous black holes we see in mature galaxies today. Their brightness in the infrared suggests they are shrouded in dust, making them invisible to optical telescopes. By measuring the surrounding gas dynamics, researchers estimate masses of a few 100,000 solar masses, far larger than expected for early black hole seeds. This challenges theories that only stellar mass remnants could form such giants, hinting that direct collapse of massive gas clouds might have played a role. Understanding these proto-black holes is essential for explaining how the most massive black holes reached billions of solar masses within the universe's first few 100 million years.
Hidden within the infrared glow of distant quasars, JWST detects specific emission lines that act as growth meters for supermassive black holes. These spectral features, such as the broad magnesium and carbon lines, broaden proportionally to the velocity of gas swirling near the event horizon. By analyzing their widths, astronomers can infer the black hole's mass and accretion rate with unprecedented precision. The observations reveal that some early black holes were consuming matter at near Eddington limits, meaning they were growing at the fastest rate physics allows. This rapid feeding explains how they could reach billions of solar masses so early, a puzzle that has long vexed cosmologists. Moreover, the data show a correlation between black hole growth and the host galaxy's star formation activity, suggesting a coevolution that began much earlier than previously thought.
Recent JWST imaging has illuminated the faint filaments of the cosmic web that connect early galaxies across vast distances. These tenuous streams of gas, composed primarily of hydrogen and helium, serve as highways funneling material into growing galaxies and feeding their central black holes. By using narrowband filters tuned to specific emission lines, the telescope captures the glow of these otherwise invisible structures. The observations suggest that filamentary accretion was already shaping galaxy morphology within the first billion years, providing a scaffolding for large-scale structure formation. This visual evidence supports simulations that predict the universe's matter distribution resembles a vast network of interconnected strands. Seeing the Webb in action helps scientists understand how galaxies acquire the gas needed for star formation and black hole growth, linking the smallest and largest scales of cosmic evolution.
Through its infrared eyes, JWST uncovers surprisingly abundant dust in galaxies that existed when the universe was less than a billion years old. Dust, tiny solid particles composed of carbon, silicates, and metals, was traditionally thought to form later, after multiple generations of stars. However, the telescope's spectroscopic signatures show strong absorption features indicating that supernovae from the first massive stars produced and dispersed dust much earlier than expected. This early dust plays a crucial role by cooling gas clouds, thereby facilitating star formation, and by obscuring ultraviolet light, which reshapes the observed colors of young galaxies. The presence of dust also affects measurements of galaxy mass and star formation rates, requiring astronomers to adjust their models. Overall, JWST's findings reveal that the universe's chemical enrichment began swiftly, setting the stage for complex chemistry and planet formation much sooner than previously believed.
Deep beneath the bright glare of distant quasars, JWST has captured vivid scenes of galaxy mergers occurring within the first 2 billion years. These collisions, identifiable by distorted morphologies and tidal tails, indicate that massive structures were already interacting and coalescing early on. The infrared data reveal bursts of star formation ignited by the mergers, as gas clouds are compressed and ignite new stellar nurseries. Moreover, the merging process appears to trigger rapid black hole feeding, linking dynamical events to the growth of supermassive black holes. These observations challenge earlier timelines that placed major mergers primarily at later epochs, suggesting that hierarchical assembly was already well underway. By documenting these early cosmic dances, JWST provides a clearer picture of how the large-scale architecture of the universe was sculpted.
In a breakthrough, JWST measures the temperature of the intergalactic medium, IgM, during the epoch of reionization by analyzing the subtle absorption features in quasar spectra. The temperature, inferred from the broadening of hydrogen Lyman alpha lines, offers a direct probe of how energetic the early universe was. Results indicate that the IgM was heated to roughly 10,000 Kelvin, consistent with heating by ultraviolet photons from the first stars and black holes. This thermal history is essential for understanding how quickly gas could collapse to form new galaxies. It also informs models of feedback, where radiation from early sources suppresses further star formation in nearby regions. JWST's precise temperature estimates thus refine our grasp of the delicate balance between heating and cooling that governed the universe's early evolution.
Finally, JWST's observations of the smallest, faintest galaxies at high redshift are providing indirect clues about the nature of dark matter. By counting how many low-mass galaxies exist at these early times, scientists can test whether dark matter particles are cold, warm, or something more exotic. The data reveal a surprisingly rich population of dwarf galaxies, which, according to some models, would be suppressed if dark matter were warm and had higher velocities. This abundance suggests that dark matter behaves more like the traditional cold dark matter paradigm, allowing small structures to form early. While not a direct detection, these constraints tighten the parameter space for particle physicists searching for dark matter candidates. JWST's deep field surveys thus serve a dual purpose, illuminating the infant cosmos while simultaneously shedding light on the invisible scaffolding that holds the universe together.
We've traveled from the faint glow of the first galaxies to the colossal engines of supermassive black holes, witnessing how JWST's eyes are rewriting the textbook of cosmic history. Each revelation not only deepens our awe but also fuels the questions that will drive the next generation of explorers. If you enjoyed this journey through the infant cosmos, hit the like button and subscribe so you never miss the next mind-blowing list we drop each week. Which JWST breakthrough resonated with you most? Share your thoughts below, and let's keep the conversation alive.